Welcome, everyone. Thank you so much for joining us for the third day in a row RAS International webinar. It's my pleasure to host this session. We'll have Carl Van Dyke as a presenter today. He has a vast experience of over 40 years in railway sector, mainly focusing on freight railways, has been employed and founded initially multimodal applied systems, then worked for Oliver Wyman, and now having his own independent expertise sharing around through to the important stakeholders. So today he'll be talking about the history, presence, and the future of operating plan control systems. So I guess we'll have a lot of great new insights to hear. So before anything else, I would give the floor then to Carl and like to invite him to give his talk. And just for everyone else joining for the first time, so we'll have a talk of about 40 minutes, and then we'll have a Q&A session. So where I would ask you to type questions in the chat, and then we'll be reading them out. And if there is real urgency for joining in orally and speaking out, yeah, we'll be fine with that. But yeah, we would still prefer having written questions as much as possible. So let's welcome Carl again, and please, you can take the controls over.
Okay, thank you. My understanding also, Nicola, is that this is going to be recorded and the presentation will be posted to the RAS website. Is that correct?
Exactly, yes. So indeed, thanks, Carl. So the presentation and the video recording will be available at the RAS web pages after the session. So, and we'll also send an email just as a notification when it's uploaded.
Great, thank you. Morning, everyone, or afternoon, depending, I guess, on where you are. I don't know how many great new insights we'll have, but we'll certainly try to take a little bit of a trot through history and current state of things and where control systems may go. So our focus today will be on what are often called car scheduling or trip planning systems and how they interact with all the different elements of a railway. So the scope then includes how shipments should be routed using what we'll call the blocking plan, and we'll come and do a little more definition of that later. Also within that scope is the definition of each train in terms of mission, how it gets routed, what its work plan is, timing, and so on. From that, the trip plan or itinerary for each shipment, and then deriving from all of that information is information on workloads for yards and trains, requirements for crews and locomotives, and of course also customer service levels. So first we'll talk about the evolution of the existing systems and look at the core logic that they use. And then from there we'll talk about how those fit against current mix of business on the railways, and from that what we might learn about potential future directions. We may or may not get to section 5 depending on timing, where we could dive in a little deeper on a few of the specific areas. But as we pointed out, the deck will be uploaded. So if we don't get to that material, it will still be posted eventually. So how do we get to where we are? So basically, information systems that are used really came around in an evolutionary process over time. And we'll go through each of these 5 levels. But they were basically sort of stovepipe systems addressing specific issues. And they had a sort of batch process legacy in terms of how they were developed. And I'm talking primarily about North American systems, but based on my experience, you'd find the same legacy and issues in, for example, the former Soviet Union systems as well. So each subsystem was generally independently designed to address a specific issue. And as we went along, things became more complex and more integrated. In this scheme, most of the North American railways are at what I would call level 5. Large railways outside of North America are generally actually at about level 4 in this, though some are lower. Often you'll see that even in the more sophisticated systems, that the local service is not still, even to this day, that well represented. And the only railway I know of that's really substantially gone past level 5 is Green Cargo in Sweden. And if we have time, we'll talk a little bit about them. So at the beginning of this all was really focused on the timetable. We had train schedules, and how do we computerize and manage those train schedules? It didn't have anything to do with shipment routing, didn't have anything to do with scheduling or itineraries, et cetera. It was really focused on the dispatch and management of the trains. And so that was sort of the baseline level that people were really starting to focus on, really on back in the 60s and 70s. At the next level, we started to introduce what I called point-to-point consisting. So this is the idea of the advanced consist. And originally, these were actually teletypes or telexes, where when one train was dispatched from a yard, they'd telex to the next yard and say, here's what I'm sending to you. So it was a fairly logical thing to start automating that and computerizing that. But you still had basically local yard inventory systems and local knowledge of what to do, but very little broader network visibility in terms of what's going on, where things were, and so on. So that was really the baseline. What things started to truly change in this process was with the introduction of railcar location databases. So where are my rail cars at any given moment in time, and tying that to waybills. And that's really the core initial base for managing the railway, is this notion of the rail location or movement database. Often, originally manually entered. There were various attempts over the years to automate that. In North America, it wasn't really until we put in the automatic equipment identification, RF tags, that truly became an automated process. And prior to that, there were lots of rooms at rail yards with clerks looking at videos of trains passing by cameras and checking them against the consists and entering the information and so on. And surprisingly, a lot of railways outside of North America are still basically at this level. They don't have a centralized blocking or marshaling plan. They do track where their cars are, but everything else is pretty locally controlled. The cleanest example of that, at least most recently that I'm aware of, is the Swiss railways, which basically operate at this level. So there's still no visibility of location to customers. There's no trip plans. There's no ETAs, and so on. So the next level is to basically introduce a centrally maintained marshaling plan, which defines what each yard is going to do, what groups they're going to make, how they're going to route the cars, and control that into a yard management system at the yard. So you've got the information from the car movement system, which we just talked about. You're combining that with the marshaling plan system. And so now you can truly start to manage how things are routed in a more unified or network level basis, and make sure your instructions are consistently disseminated across the network. Strangely, or I don't mean strangely, but interestingly enough, one of the biggest impetuses in North America to do this was to get rid of routing clerks. It was really a labor savings effort as much as it was a technology effort. When I first came in on the working on the railway, I remember being at the Burlington Northern in probably 1981 or 82, and that was their big push. Let's get rid of the yard clerks, the routing clerks, and automate this through a centralized marshaling plan. So this system that we're looking at here was basically conceived and first achieved by the Southern Pacific in the top system in the early 70s. And many other railways adopted that system. I don't know the full history, but there were direct copies in use at places like Missouri Pacific, Canadian National, and Burlington Northern. And it was really the core foundation in terms of conceptual design for how to define the marshalling or blocking plans at the railways. This is the level that, for example, all the former Soviet Union railways operate at today. And I believe, unless something dramatic has changed, China, for example, also operates at about this level of technology. So sort of the final piece, really, for our existing technology really was created around 1980, which tells you how little maybe has changed in the last 40 years. And that was the introduction of the car schedule or shipment schedule. And that was done to take all the pieces that we've talked about and bring them together. You brought in the timetables, you brought in the marshalling plan or blocking plan, you brought in the movement data, and from that you tried to figure out what the itinerary was for every shipment across the trains, estimate their arrival times, and so on, which then in turn could drive the ability to produce projections on shipment status to customers, future yard inventory and workloads, and train sizes and consist projections. And this was really built by the Missouri Pacific with Federal Railroad Administration funding in the late 1970s, early 1980s. So this was up and running at Missouri Pacific probably by 83, 84 in a consistent manner. And it was actually then incorporated and became the UP system post the merger with the Union Pacific, and what is today called the TCS system at Union Pacific, still running on code that came from the Southern Pacific circa late 60s, early 70s. At one time, this system was then used at a number of other railways. It was sold to Germany, it was sold to India, it was used by the Mexican railways and so on. That's largely gone away and been replaced by newer versions of these systems. But UP is still using this system and in the process of trying to replace it. Despite this being up and running in the early 80s, it wasn't really until the close of the 1990s that all the other North American railways anyway had achieved this level of sophistication for various reasons. By and large, all the North American railroads use a variation of the technology that was developed in this system. Some of them are direct linear descendants of this system, and some were new built, but the fundamental technology in terms of blocks and connections at yards and time scheduling of cars and so on is basically the same across all of the railways. And really the notion in all this is that shipment schedules could be the key to operational management of the railway. So you think about the itinerary of a shipment, you think of it two different ways. One is a series of trains the shipment's going to go across, and the other is a series of connections that the shipments are going to go through with the yards. So slicing the data in these two different ways, if we add shipments across a train, obviously we can see the future projected volume and workload and plan for that train. If we add all the connections across a yard, we can see projections on the workloads of the yards. And if we look at the linear end-to-end process or the itinerary, we can start to provide projections of estimated times of arrival to customers. All this is great. It's got a couple of issues. One is that if the railroad doesn't execute the plan as stated, all of this information becomes increasingly unreliable. And so that is actually, in fact, an issue that reduces in many ways the usability of this information. The second is that this looks great from a perspective of a carload or conventional shipment that's going through multiple rail yards, but is not so well aligned for things like unit trains and is only moderate in its alignment with business lines like intermodal. So if you bring all the pieces we talked to together, you get a diagram that looks something like this. At the top, we have the operating plan, and it's really got two major pieces, the blocking plan or routing plan, and then the train profiles or what trains you plan to run. And that then in turn feeds into the real-time systems that are based around what I'd call a dated train database, which is the actual instances of trains you're going to operate across the railway. And then the railcar movement database, which has got a mix of your waybills and the current location messages for the rail cars and the shipment schedules or itineraries for each shipment. And that in turn then can interact with a variety of other systems focused on operating the trains, dealing with locomotives, dealing with crews, projecting forward train consists, yard inventories, thinking about empty rail car distribution and so on. Again, I keep tooting and saying over and over, great for carload, maybe not so much for other lines of business. Over the years, of course, these have then been enveloped and developed into more complex environments where you're bringing in all the other pieces of the puzzle and integrating them in, both directly with things like T&E, train and engine, payroll, and car hire, interline settlement, revenue management into the waybills, but then all sorts of other ancillary systems that are dependent on this, from intermodal to shipment costing to how do you deal with line of road maintenance and how that impacts schedules. How do you communicate with other railways? How do you communicate with customers, and so on? So the systems become embedded as the center of very, very complex systems. And that becomes an interesting challenge, because when you go to try to replace one of these systems, it becomes very tricky because of these massive interdependencies. So a number of railways have been engaged in multi-year efforts to replace these systems. Union Pacific, I know, has been at it for well over 10 years. I know, for example, other railways are, at various levels of multiple years and of stage and incremental replacement of these systems, because they were all basically written in, traditional mainframe code anywhere from 20 to 50 years ago. Harder and harder to get developers, less and less flexible, less and less aligned with modern platforms, modern communication systems, and so on. And it becomes an interesting issue, but it's also an opportunity, because as you go to replace these systems, you have the opportunity to change and think about how could you redo them and realign them for current modern needs. So now we'll spend a couple minutes just talking about a few of the details of how these systems function. And what we mentioned, the core piece of this, ultimately, when you build all the parts together, is the car scheduling system. And what does that do? That basically tries to figure out what the itinerary of each shipment is. And from that, it then provides all the things we talked about: projections of train size, yard workloads, customer service. And it's a fairly simple process at most railways. It starts with selecting a block, and we'll go into more detail what a block is, but for now, it's a group of rail cars that are going to be moved together from one yard to another yard. So a rail car is at a specific yard. It goes through some process to select the block it's going to be assigned to depart that yard. Each train, in turn, contains a set of block assignments. So what blocks that train should carry. And so you can go into a table and you can look up all the potential trains that could take that block. And through some set of business logic, we select a specific train to depart the yard on. So that's the second step, select train. And then using that, we can advance the shipment to the next yard and ask the question, are we at destination or not? If not, go back and repeat this process until we do reach destination, at which point you have a complete trip plan. And that is the core logic that is used at current across all of these various systems at different railways. To make it work, as I mentioned earlier, you need a well-defined blocking plan that can be interpreted accurately by the computer, where the plan is followed by the field. If it's not followed, then the trip plan is not going to be correct. Second, you need a well-defined train schedule, including rules for which blocks will go on the train. Again, where the plan is followed by the field. I keep emphasizing that because the process is very dependent on a consistency between actual operations and expected operations. Important to note in all these systems in the present is that there's no capacity constraints on them. So you can oversubscribe a train. You can oversubscribe a yard. And basically what happens when that occurs is that some amount of traffic gets left behind because the train is full, for example. And that traffic then, quote, rolls or delays to the next available train, again, causing the trip plan to be, in that case, inaccurate. But it also means the system is somewhat self-correcting, because every time something goes wrong, it just falls back into the scheduling process, attempts to reschedule the train to meet that. The train schedules can be dynamically changed in this process. The real-time trip planning system is always going against the dated train schedules, the ones that are reflecting actual operations. And so as the schedules change, the trip plans can be updated to reflect those schedule train changes, as long as the railway is doing a reasonably good job of projecting what those revised schedules look like. And as I mentioned in the bottom, the self-correction process is very important, generally referred to as retripping when the plan is no longer accurate. So basically the process runs through what we'd call a cutoff process. So here's in this little chart on the right, you see the train arrival, and it's setting off some set of cars that are going to go on an outbound train. There's a minimum processing time that is designated as the cutoff or minimum time to make a connection. And so it's going to say, well, the car can't go out until that processing time has elapsed. So in our example, train number 1 is too soon, and so it misses that. It's now ready, and so there's some amount of waiting time, and then the train, it then departs on that next train. Should you miss a connection, then you simply delay until the next available train option becomes available. And so those define then both the impact of a missed connection and the average or overall processing time. So in a simple example, if we have once a day departure of the outbound train with random arrivals and a 12-hour minimum processing time, then your average wait time would be 12 hours, 1/2 of the headway between trains, and your processing time is 12, which gives you a 24-hour average time in the yard and a 24-hour cost for delay. And that gets you to think about things like, if you doubled the departure train frequency, you would cut the delay time and the wait time in half, for example, improving your reliability and your transit time. All this is, of course, predicated on the notion of the blocking problem or routing rules for traffic. As we mentioned, a block, in technical definition, is a group of diverse rail cars with various origins and destinations that are moved together as a group from one location to another. So in this little simple diagram, we say we just made the 5 blocks shown, A, C, B, C, C, D, D, E, D, F, and we're at A. Then at A, we would put all the traffic for all the other destinations in a block going to C. At C, we would reclassify these cars, and those going to D, E, and F would go in that block. And then at D, the F cars would go in the F block. So it's this regrouping process. And the idea is that you don't have enough traffic to run a train direct from A to F, but by grouping traffic, we could build up a larger train and route the cars through the network in a way that hopefully is reasonably efficient. But you do pay the cost of the intermediate switchings. And so there's always this trade-off of block size, train frequency, and switching to make things work. But it really means then that the efficiency of the network is, for carload anyway, is determined in large part by the blocking plan because it determines both the number of times the wagon or car is going to be handled and how direct the routing is and so on. And so, key decisions in this become what blocks should be made at each location and what traffic should be put in each block. And then that therefore drives the routing process. Combining that, as I said, with the trains gives you the shipment schedules. And, that then in turn drives the reliability and transit time for carload because it's really at the yards that the connections are made and where connections are missed. And introduction of reliability issues comes and drives heavily that, particularly in North America. And as we talked earlier, we have this notion of daily departures driving about a 24-hour yard time for cars. And so quickly you get into these things where the percentage of time for a merchandise car is really in the yards, where 2/3 of the time might be in the yards and only 1/3 actually at a customer moving in a train. A lot of effort is spent on thinking about that. Most systems, blocking systems, run on a lookup table where there's a series of rules, and the rail car for a particular yard at a particular yard hits those rules, and from that it determines which block is used. And the rules can get quite complex, particularly for defining local traffic and specialized moves, and have some issues with flexibility as well. Alternative to that is to use algorithmic blocking. And the basic notion is that you can form a network from the nodes, where each block then becomes an arc in the network. The nodes are the yards and the arcs are the blocks. And if you have that, then you can use a number of methods, but primarily some form of weighted shortest path to find the best block sequence across that network. You still need rules and cost weightings that capture the mission of each block, determine its eligibility to carry a specific shipment, and so on. It's important to remember that blocks are not trains. Only when you assign a block to a train do you have the movement of that block. The blocks in and of themselves have no day of week frequency. They don't have schedules and times associated with them. Algorithmic blocking is currently used at Norfolk Southern and now at Canadian Pacific and CSX. And as I said, the basic notions are first, which blocks can the traffic take? So in this little example, if we're going from O in the upper right to D in the bottom left, we might say, oh, well, block CD1 is not allowed to use this block. So we essentially take that arc out of the network, and then we associate a cost. In this example, it's done with kilometers to each block, look for a shortest path. In this example, then going from origin to location A to location D would be the shortest path. And in that case, that would be the block sequence that would be used to get from O to D. And that's the basic, simple, high-level notion behind algorithmic blocking. So that's all the parts of the core parts. There's crew scheduling, locomotive scheduling, so on and so forth. But the core, again, is train schedules and blocks within the context of the carload process. So things have changed over the last, well, from 1970 to current. So over the last 50 years. And so does this all still make sense? So I think we really need to think about what are the primary lines of business in a modern railway, particularly in North America in this example. I know this is 2008, and quite frankly, the numbers probably haven't changed. Intermodal's grown, coal has shrunk, agriculture's grown, carload has probably shrunk a little bit. By and large, these are pretty close to indicative. And it shows you there's like 5 major areas of business. There's coal, which is largely unit train, agriculture, which is partly carload, partly unit train, intermodal, which is largely dedicated network, automotive, which is a mix of dedicated network and some on intermodal and carload, and then the carload network. So it's a much more complicated picture than it used to be. And so you have to ask the question, how does that business mix fit with this carload-centric control system that most railways have? And what you quickly discover is there are pieces that still fit quite well. I think there's a good match with traditional carload, obviously, and a lot of multi-block automotive fits pretty well, but then things get weaker. Intermodal, really what you are routing are the containers and trailers more so than the rail cars. Some railways have adapted this to generate container and trailer-based trip plans instead of rail car-based trip plans, still using the same principles, and those work moderately well. There are some other things like gathering processes for grain and for empty multi-levels that kind of work, but then things sort of get a lot worse after that, for lack of a better term. And in particular, for all of your solid trains and unit trains, it's really a Band-Aid approach, and there are a manifest number of issues that arise because of that lack of fit with unit trains. And often either railways turn off the system when it comes to processing and handling unit trains, or accept that the information is not very useful and have built other systems up that try to get around the shortcomings in that area. So basically the question arises, is it time to rethink the core functionality of these systems? And so with the rise of unit trains and intermodal, the systems are really only oriented to meeting less than 50% of a railway's traffic. We kind of covered most of this, but I think unit trains are probably one of the best examples in all this because the trip planning functions don't apply very well to unit trains. Unit trains generally are released to move on a specific train on a specific date as a group. And if you try to put that traffic through a blocking system and then glue the blocks to that train, you're trying to indirectly associate the cars to the trains, and all sorts of bad things happen. The cars can miss the unit train entirely and drop into the carload system, polluting the information and data in the carload system, or they can get glued to the wrong unit train, or other traffic can get glued to the unit train. Various issues like that constantly arise. And the other is customer ETAs. The customer wants to know when his traffic or train is going to arrive. The carload car scheduling system is built around handling yards and tends to update the trip plans or car schedules each time a car is handled at a yard. It doesn't so much report updates to the trip plans when trains get ahead or behind schedule, except to the extent that those ahead or behind schedule events cause a retripping of the car. Well, if you only ride on one train, there's nothing to ever trigger a rescheduling of the car. And so the car scheduling system does not produce updated ETAs of any value. And literally what many railways have done is said, well, we can't solve this problem, so we'll just tell the customer where his train is at various times and let the customer run some statistical models to try to guess when the train might actually arrive. There's also issues around local pickup and delivery services, also requiring a lot of intervention and manual guesswork to plan those. And there's lots of other examples. So the only other comment I want to make here is that as people rethink their production systems, what I'm finding is they continue to be very focused on this carload model and are having a hard time getting outside of the box of that model to think about their total business. And so I kind of think of the carload model as holding undue influence on the design of new solutions. We still need a carload model. We still need that capability, but we need additional capabilities that will address the rest of your business, the rest 50 to 70% of your business that doesn't necessarily fit well within the carload model. So what that really means is we need this evolving focus and evolving system requirements. And to effectively meet those, I've sort of highlighted some areas. So some of the ones that are not highlighted are things that are already addressing within the existing design. But stuff that does need to be started more focused as you build new systems: empty rail car distribution, unit train planning, gathering networks, capacity management, intermodal, resource management, and so on. All of these, I would argue, as you re-platform a system, have to be a focus. So what does that mean in terms of future directions? I'll just run through some examples, and then we'll go to Q&A, I believe. One area which stays within more of the carload model is more sophisticated car scheduling logic. Algorithmic blocking we talked about is becoming increasingly adopted, and is certainly one piece of that. But there's also a lot of notions around dynamic scheduling where you can take a more time-space oriented approach. So your arcs in the network are no longer just point-to-point time-independent blocks, but are instead train blocks that move through both time and space. And you can start to think about routing across train blocks on a more dynamic basis so that not every rail car between the same OD may take the same physical route or same train route or even same set of blocks, but with limits on excess car miles, you can certainly come up with some more sophisticated things, which then could lead you to the next step, which is looking at capacity management and yield management, where you can say, oh, if a train is full, maybe we could take a different block, a different train that still has space on it, and advance our car more quickly than we would taking a strictly static blocking plan view. And so then we would be tracking capacities and then either simply rolling traffic to later trains or having alternate route generation when that occurs. It's hard to do this unless you have very good knowledge and understanding of the trains you're operating and the reliability and performance of both your trains and your yards. Only one railway that I know of on the planet is doing a booking and capacity management system, and that's Green Cargo in Sweden. They have the advantage of being somewhat small in terms of scale, but also they operate at a level of something like 95% on-time delivery with zero lateness tolerance. So very, very reliably run railway, but they do full capacity booking at the time the customer books their shipment, including scheduling the empty rail car into the customer in advance and designating what time that car will be released by the customer, with late penalties on the customer if they don't hit the window, and a requirement that the customer load the specific destination and the specific car number that they were handed for that purpose. So very disciplined operation. The Germans have to some extent tried to copy and mimic aspects of that with mixed success. I'm not really aware of anybody else doing booking at that level. Intermodal shipment and ramp management systems. Again, we need to really think about what the relationship is between the rail cars and intermodal units. Rail cars, particularly when they start switching intermodal units between rail cars with lift-on, lift-off operations, really are decoupled from the movement of the boxes. And so we need to have a better understanding of how to schedule those. And we also need to have a better understanding within the scheduling systems of when you're doing rubber moves and rubber interchanges versus steel wheel interchanges. Unit train equipment cycling is very weak at most railways in North America. We really need to start thinking about train sets, tracking and scheduling the entire consist across empty and loaded cycles, moving away from the car scheduling logic, and taking a much more simple approach that says, gee, we know this group of waybills, this group of cars is designated to go on this train on this date from this location to this location, and just leverage that information directly to associate cars to trains, and then in turn rebuild the ETA processes for customers around the trains and not the cars to make everything work and flow more reasonably for that. I think it's generally not done, or only to a limited extent done, where we're looking at the entire train consist across multiple loaded empty moves in North America. However, there are great examples in Australia, to some extent South Africa, and possibly in Brazil, of systems that have been built up that are very focused on the consist level routing and management of these train movements on both a mine to port and mine to utility basis. Another area that needs more development is tactical decision support systems. This includes both looking at the impact of tactical changes to trains and blocking when they have to be made. The classic example is a yard is completely plugged and you've got to divert a train or two to a different yard. There are ways you can start evaluating which trains make the most sense in terms of cost and impact, and can be addressed in that way. Another one which has kind of come out of the PSR movement is this notion of dynamic bypass blocking, where you get these large slugs of cars. The classic one is a large slug of grain cars out of an elevator, say 20 or 40 cars, not big enough to put in a unit train, but it's sort of the python swallowing the elephant. It becomes this big lump moving through the network that causes issues. You don't really want to bust the cars up, but they often do get broken up to fit into size trains. So how do you manage that without disrupting your train network and without disrupting the other traffic on the network? Can you find a way of moving that as a slug by doing some kind of analysis of the trains you have available and the space on those trains and so on, implying again some ability to look at capacity. And you'll see that with like interchange receipt also. The classic is potash coming out of Canada, which goes as a solid train in Canada, but then atomizes when it hits the interchange to the US roads into large chunks. Others, automotive empty rail car management, where the multi-level system don't tell you where the rail cars are going initially, but you've got to gather up these empties and then dispatch them in loaded trains. Relatively poor information and support for those sorts of situations. Tactical train management. Currently, most of the train schedules in North America, better in places like Europe where they have train slotting, are not very realistic in these systems. When a train is early or late, they just ripple the times forward or back to reflect the change, but they're not taking congestion into account. They're not taking the impact of interaction between other trains into account. When you launch a unit train, it's just, you set the start time and it just develops all these intermediate and arrival times that have nothing to do with track capacity. If you could improve that process, you could improve the quality of the trains in the dated train database, which would drive better management of crews, better management of yards, better management of locomotives, and better ETAs for customers. And then finally, there are a lot of different models for how to define the gathering and distribution network. These are generally band-aids in most current systems and really need to be thought about deeply when the systems are rebuilt to better align them with how actual operations function. And oh, I'm sorry, I'm doing local service. This is gathering distribution. This is the notion of gathering up groups of blocks of cars to then run a solid train. So this could be 5 days of releases out of a steel plant that then turn into a unit train, or this could be groups of grain cars going to Houston that you gather together to run a solid train. And how do you support that? How do you support empty equipment and customer order management? In particular, do you go to someplace like Green Cargo where they, book you can't get an empty without identifying the loaded outbound, and so you tie a relationship between the empty management and the loaded management and your future projections of network workload and so on. And then finally, product catalog concepts that look at what are your service offerings, both within carload, but intermodal and other lines of business. How do you communicate that to customers? And how do you ultimately tie that to pricing and contribution, alignment with your network design, and whether particular shipments are good ones or bad ones in terms of fit and what your offer should be to customers. So I think I have gone a little past the 20 minutes I'm supposed to allow for questions. And so I will, I think, stop at this point. I do have a number of examples, but I will, those will go on the upload. So at this point, Nicola, I think I'm going to stop, and if you want to go to questions, we can do that.
Yep, great. Thanks a lot, Carl, for the super formative presentation and giving a lot of great details. So we did get some comments already. through the talk, so I could start with that. And there are a few from Marty Schlenker. I hope I didn't do too bad on that.
Oh, you did great on his name.
Okay, great. Thank you. Thank you. I was a bit afraid of doing it terribly wrong. Okay, so one of the comments he has is that indeed that DNSF is also in the middle of the modernization, and it actually takes 10 plus years of effort doing it. So there's a comment, and I would continue with a question. Are those expected durations that we shall foresee for changing, and what is the end point if it exists? And maybe to add as how to secure that our final product is not outdated already.
Yeah, the last question, I'm not sure I can answer. That's a tough one. You only know what I know in terms of observation. I mean, what I've seen of other class ones, you know, most of them are taking an incremental approach, trying to replace their production systems in pieces, where they feel they can take a particular subsystem and hive it off into a new platform. Of course, that causes some integration issues back to the main platform. But as we said, these systems are so complex, and the cost is so high to replace them, that from both a financial management standpoint and from a risk management standpoint, I think, yeah, 5-15 years, anywhere in that range, is not an uncommon conclusion. But it also means that you really have to think about all of these system replacements as part of a continuous evolution, where you know, you're always going to have elements that need to be replaced. One of the goals in many of the replatforming processes is to make the systems less monolithic and more modular in their system design, so that you can replace them one piece at a time. And so that you can get into a more evolutionary process once you've got the basic re-architecting of the systems completed.
Okay. Okay, I see a new question coming from Dasarat. It touches upon Japanese railroad operating practices, and asking if they excel on the same degree regarding freight as passenger railways. And here I would expect that the question is more related to high-speed railways. So if you have the knowledge about it, could you say something about?
I'm not sure I fully understand the question. My knowledge, to be frank, on Japan is somewhat limited. On the freight side, they have largely moved away from having really any meaningful carload traffic. They've moved heavily to kind of containerized processes for most of their freight traffic. I'm not sure what that does in terms of relates to train speed. The Shinkansens run on dedicated network that have no freight. I'm not quite sure where to go with the question, I'm afraid.
Yeah, so what I can add on that one, when it comes to Japanese railways, people often get impressed with performance, which is high-speed railways. But if we talk about conventional passenger rail, that is actually pretty much on par with European railways. So there is not much difference there.
Yeah, I've been to Japan. I've ridden both the freight and I mean, not the freight, the high speed and the conventional trains. And the conventional trains rock and roll along just like everybody everywhere else. They're not anything special that I could see. So I'm not sure
Yeah.
that's, yeah, I think we should move on.
Okay, yeah. So there's another question from Hadi. Karimi, he is asking if you could give some more details about Sweden and how they gone beyond the level 5 maturity.
Okay. So um, Sweden has moved to a fully booked capacity reserved system. So each train um, is got a known length, maximum length, and within that train there are multiple blocks. Typically, there's an anchor block, which is the primary mission for the train, and then one or more secondary blocks. And so they provide an allocation of capacity to the anchor block and the secondary blocks. And for the for both, they have both an overbooking factor that's allowed. In other words, can you book more wagons than the train can actually hold? And then they also have, I'm not sure what the term would be, but basically, can one block grow if another block is undersubscribed? So they have a bunch of capacity allocation rules for the blocks on each train. And they manage a perpetual reservation system that knows at any moment in time all of the wagons booked to each individual train. When a customer wants to move a shipment, they contact the railway and say they want to move a shipment from A to B of this type of rail car and departing the origin on such and such a date. The system goes out and checks the capacity that's available on the trains and also checks the availability of empty wagons. And in the good scenario, it says, I have this empty wagon, I can get it to you in time, and we will book this shipment across this train or series of trains against the capacity that's available on those trains with a departure date and time of X. And we will get you the empty, which is also scheduled in based on the available capacity. We'll get you the empty on this other date, some amount of time in advance of the departure, typically only about 24 to 48 hours at most in advance. And so that's in the good scenario. In the not so good scenario, we might come back and say, oh, we can't get you the empty until this date, so can you delay and will you accept this delayed arrival of empty and delayed departure of your shipment? Or the converse is we don't have outbound capacity, will you accept your departure being delayed to this other date? And so everything gets scheduled against the trains. It also means, though, that you could have a shipment sit at an intermediate yard. So when they operate, when the train comes in, you could have 3 cars going to the same destination, but 2 are booked for today's train and 1 is booked for tomorrow's train. The car for tomorrow's train will get set aside and held for tomorrow's train. The only exception being that there are people who manage and track the real-time fill rate of the trains and may choose to advance the car on an earlier train if for some reason other things have gone wrong and there's capacity available. But by and large, it's trying to run this kind of airline style fully reserved system. Their connection rate at yards is in the high 90s in terms of percentage. Average yard times, because everything is scheduled inbound to outbound, you can fleet your trains in and out. So yard times are 3, 4, 5, 6 hours opposed to 24 hours. And their final arrival at customers is running around 95% of the time on time or early with 0 lateness tolerance. So there are entire decks. There was a deck presented to X-Rail that was at one time publicly available that goes into a fair amount of detail of how their system works.
Okay, thanks a lot for a very thorough explanation. So Now come back to PSR. So what, if any, impact it had on the requirements for the new planning systems?
That's a very interesting question that I can't fully answer. At the surface, PSR is pushing to have less single-purpose trains and move more in carload. So in some ways, it raises up the importance of the carload style network. So for example, it says a number of railways would run ad hoc unit trains. So an ad hoc unit train, for example, would be, I've got a steel mill and it's shipping a lot of material to some other single location, but it's only releasing 20 cars a day of traffic, and we won't want to run a 100-unit train. So we're going to accumulate those cars over a 5-day period and then run this 100-unit train. If you look at it from a car cycling standpoint and a yard capacity consumption standpoint, it's a pretty awful process because a lot of these cars are sitting around for a long time. So it tends to push that kind of situation into the carload network, which kind of says that continuing the carload design and its importance remains. However, it's also continuing to drive a bunch of decision-making in other parts of the railway. One in particular is it's making many more demands on the local service and smaller yards to do more refined blocking and scheduling of the rail cars and demanding higher precision in terms of connections. And so when I mentioned that the design support at the local level tends to be fairly weak at a lot of these systems, that's an area where PSR would demand much better defining of local service and how it works. Similarly, it has much higher demand on being able to do both block swaps and classifications at rail yards in a precise manner. And so additional emphasis in those areas become important. And the last thing I can think of off the top of my head is, I can think of two more. One is dynamic blocking, was a notion that's come out of PSR, where you're looking at whether you can build these mixed trains by taking blocks and assembling them onto trains on a little more ad hoc basis while still maintaining the discipline on the train schedules. And then finally, if you're going to do some of the more clever things with train schedules and crew management and swap crews and so on, then you really got to get better about maintaining their dated train schedules and their accuracy. And so that will be another impact area.
Okay, great. Thanks a lot. So given the time, unfortunately, we couldn't go through all questions. See, we have a few more great ones, but yeah, we have to save that for after the seminar. I'd like to use the opportunity to thank once again to Carl for a great presentation and for the wonderful participation from all of you. So if you have your questions still open, we are all open to answer. You can either forward them to me and we'll share it with Carl, or email Carl directly. After the talk, in the next day or two, we'll have the slides and the recording available online. So thanks again, and we are preparing more talks for the coming months. So we hope to keep in touch. Great. Thank you so much, and have a great day.
Thank you all.
Thank you.